All right, ladies and gentlemen, welcome back to another video with Mr. Kenton. This is AP Chemistry, and we're working through Unit 5, and we just finished up with our discussion with half-life and experimental data and how we can use that to determine reaction orders. And so now we're going to dive into more of the mechanistic components of kinetics by looking at what we're going to call elementary reactions and how we can use elementary reactions to help us to develop rate laws for an overall process. Now, again, up until now, the only thing we've been really looking at is with the reactants and the products, like step 1, step 2, final and initial. We haven't really been examining the path that the reactants actually took to become products. Well, so that's where mechanisms are going to come into play, right? And because a reaction mechanism is going to show us a possible pathway through which a chemical reaction is going to take place so that it can end up at the product stage, right? And so it's important to recognize that mechanisms, they're a useful tool, but they're not absolutes, okay? Now, what a mechanism can do is it can provide us with a detailed picture of the bonds that are being broken, what bonds are being formed as this process is taking place, right? Because if you think about it, that's really what chemical reactions are. Essentially, there's bonds that are being broken, and then there are new bonds that are being formed over the course of that particular process. And so our mechanism will provide us a very detailed picture as to which bonds are being broken and which ones are being formed. Okay, now an elementary reaction, how are we going to define that? So I think the place for us to start with is simply to say that an elementary step or an elementary reaction is going to be one step within a reaction pathway. So if you've got 3 or 4 steps in a reaction pathway, if you just isolate and look at one of them, that individual step would be an elementary step. Okay. And we can play this out by looking at this particular example. Let's say we consider the reaction of nitrogen dioxide plus carbon monoxide reacts to produce nitrogen monoxide and carbon dioxide. So that's the reaction. That's the entire process. That's what we've been looking at up until this time. Well, let's say that we're given a mechanism that's made up of 2 different steps. This process happens, these products are formed through 2 elementary steps. And so we can see that the first step is going to be our nitrogen dioxide interacting with another nitrogen dioxide, and it's going to produce nitrogen monoxide and nitrogen trioxide. The second step of this process is going to be nitrogen trioxide interacting with carbon monoxide, and in doing so, it's going to form nitrogen dioxide and carbon dioxide. Okay? And if we're thinking about this from the perspective of kind of our steps, and just to be pretty clear here, right? So this would be step number 1 right here. So this is step 1. And then the reaction below that would be step 2. Now, when you add up those 2 reactions, you end up with a total sum of 2NO2 plus NO3 plus CO produces NO plus NO3 plus NO2 plus CO2. Now, if you've been following along and you're looking at this, you're thinking, okay, well, it looks like there's some things that can be canceled out. And that's absolutely the case, right? We've got this nitrogen trioxide that shows up as a reactant and as a product. We've got a nitrogen dioxide that's here. That's going to cause this coefficient to change. So instead of that being a 2, we now have a coefficient of 1 in front of our NO2. And we can do that, right? If we can simplify it, we're going to do that. And so when we do that, we simplify, we eliminate those substances that appear on both sides. And once we do, we're able to see if this turns turns out to be matching up with our original reaction. So when you look at what we're left with here at the bottom, we've got NO2 plus CO produces NO and CO2. That does in fact match up with the original reaction that we had. Now, you might have noticed that there was this one substance, NO3. Showed up here, and it showed up here, right? So NO3 is going to be a substance that we're going to call an intermediate, right? And it's an intermediate because it shows up in one step, but then gets immediately used up in the next. And it's not a part of this overarching process for this chemical reaction. And so it appears, but then it gets removed pretty quickly through that particular process, right? And for it to be an intermediate, it cannot be a reactant or a product, right? Because if you look back at our original equation, we didn't have any nitrogen trioxide. So that's how I kind of knew, wait a minute, that's probably an intermediate. Now, within your elementary steps, it's going to be important to be able to identify what chemists call molecularity. Sounds like a really convoluted term. But what it simply means is you're going to look at the number of molecules that are present in an elementary step, right? And it's regardless of whether they're the same molecules or not. And it is important to note that we're going to be focusing in on the reactants. So the number of reactant molecules. So number of reactant molecules present in an elementary step, right? So you got unimolecular, which means you have one molecule in your elementary step. Bimolecular, which means you have two molecules in your elementary step. Termolecular, which means you have three molecules in your elementary step. And just as a note, termolecular processes are very uncommon, not impossible, not non-existent, but what we start to see, and we'll learn about this later when we look at collision theory, is that it becomes statistically improbable for effective collisions to occur when you have a termolecular process, okay? And so when we look at kind of what's been listed here, you've got three different steps or three different elementary reactions, and we can see here that the first one's bimolecular because you got two molecules. In this case, they happen to be different, so you've got ozone and oxygen atom. For the next one, it's going to be bimolecular because you've got two nitrogen monoxide. And so those two nitrogen monoxides, even though they're the same, it is going to count towards that number of molecules that are on the reactant side. So it'd be two, so it's bimolecular. And here we've got the decomposition of ozone. Since it's only ozone, it would be unimolecular, right? So that particular elementary step would be a unimolecular process. Okay, and so just, again, make sure you just look at the number of reactant molecules present in your elementary step, and that's how you can figure out molecularity. All right, now let's take that information, understanding that we've got these different types of elementary steps. How would we determine rate laws from elementary steps? Right? Now, the nice thing about elementary steps is because we're assuming that this process occurs in one step. So for that particular step of the reaction, that's what the rate of it is going to depend on, is how does this step take place. And so what we can do is we can use the stoichiometry of an elementary step to determine its rate law, right? And maybe a better way of saying that is to theoretically identify what the rate law would be for that step. And we can do this because of the law of mass action. And the law of mass action states that the rate of a simple one-step reaction is going to be directly proportional to the concentration of the reacting substances, right? So there's going to be this correlation between the rate and the concentrations of the reacting substances that are present. Now, so when we start to look at this, we can look at elementary steps and we can identify what their rate laws would be. Because these are all elementary steps, we can simply look at the stoichiometry and the coefficients of our substances to determine our rate law. So for that first unimolecular process, you just have the reactant A, so rate's going to equal K times A. For bimolecular, you see there, since there's two A's, it'd be K times A squared. For the other bimolecular process, you've got K times A times B, because you got a coefficient of 1 in front of both of those substances. And I think you guys are seeing the pattern there, and so I'm not going to spend a lot of time looking at the other three. Now again, just want to draw to your attention here that because we're dealing with elementary steps, this is where we can use the coefficients and allow them to be exponents in our rate law. Obviously, this is a little bit different than what we were doing before, but we're within the context here of we're dealing with elementary steps. In our previous example, we weren't dealing with elementary steps. We were assuming that there were multiple steps that were taking place, and so we were trying to account for all of them to come up with our overall rate law. And then the last thing we just need to take a look at as it pertains to elementary steps has to do with what's called the rate determining step. And I like to think of this from the perspective of, you've probably heard the phrase, you're only as strong as your weakest link. And so the same principle can be applied to a reaction that occurs in multiple steps. You're only going to be as fast as your slowest step, right? It doesn't matter how fast, like if you're running a relay, it doesn't matter how fast you're going. If you run really fast, your partner runs really fast, but then your third teammate, they run really, really slow, that's going to impact your overall time. Doesn't matter that you ran the first two legs really well, but then on the third one, it's slower. It's going to slow things down. And so the same thing is going to be true with our reactions. If there is one step that's slower than the other, then that's going to be what we call our rate determining step. And so our rate law will always be based off of the slowest elementary step, or the rate determining step. Now, if the slow step is the first step in the overall rate of the reaction, then it'll be based on the stoichiometry of the first elementary step. Okay? And so we can certainly use that to our advantage. If the slow step is not the first step, then you might have to add up the reactants to the slow step and cancel out any intermediates. You might even have to go through and do some other processes to make sure that it matches up with the rate law, but we'll discuss that much later. All right, so the key thing to take away from here, even if you've got a mechanism, there's going to be one step that's going to be slower than the rest. That's going to be our rate determining step. And since it's an elementary step, we can use the stoichiometry of that to come up with our overall rate law. Okay. So again, from this, we introduced the idea of elementary steps. So this mechanism, this pathway that the reaction takes place, where you can see all the bonds broken and formed. But reactions are made up of a series of steps, and each individual step is an elementary step. We talked about molecularity, so we could look at the number of molecules and say, okay, if this is unimolecular, it's going to lead to this particular rate law. And then we also looked at how determining our rate law would be based on our slowest elementary step, or the rate determining step. So thank you guys for joining me here. I hope this was insightful. If you do have any questions, please don't hesitate to ask, and I look forward to seeing you guys again soon. Take care.